Space distribution. Yes. Okay, I think we can start, although I would love to have more people in the room, and it's kind of a depleted audience also on Zoom. But let me start. Huh? आज तो पूजा नहीं है ना. Okay, so I welcome everyone again for this edition of the Wednesday Colloquium. And actually, one of the things that we typically do, and as you saw last week, we invite the young faculty members who have just joined the Institute in maybe 1 year or so to sort of talk about their work in the broader context to the entire Institute. And on that note, I have Dr. Shadab from the Department of Theoretical Physics, who joined us in 2022. So it's almost a year or so. Shadab actually kindly agreed to give the colloquium this time. And I expect all the other younger faculty members as well to come up and give colloquium talk. So before I go into this short introduction on Shadab, I wanted to tell all of you that the Nobel Colloquium will be held on November 8th. So please mark your calendars for that date. That is sort of one of the important ones where at least I want to see the entire institute coming in here, or at least most of them. And if there are packed rooms, we can do it a little bit more sort of in an online manner as well. So with that, I would like to introduce, Shadab actually joined the Institute in 2022. Currently, he is a reader in the Department of Theoretical Physics, but his training goes in a historic manner because he actually is one of the first few, and actually the second batch that carried out the BSMS program in IISER Pune when it opened in, I think, 2006, 2007. Yeah. And is one of the early graduates from that program. And it's wonderful to see that the program has done wonderfully well over years of its existence in IISER Pune. Shadab did his BSMS with major in physics from IISER Pune. Then he actually did another MS at Carnegie Mellon, CMU, where he did his MS in physics as well as PhD in physics, which he finished in 2016, and then moved to University of Edinburgh for a postdoctoral work from 2016 onwards till he joined the institute. Shadab's actual work is on redshift space distortions and looking at how to use that to look at the universe. So Shadab, without further ado, I would like to welcome you for this colloquium.
Thank you. Thanks a lot for that kind introduction. I'm really pleased to give this talk today. And then I realized as I looked at my own slide that the color of this is not something I made it like this. It's because of the projector. So the green color is all missing. So many times you'll see that there is more blue than green. That's because projector is not working properly. Apologies for that. So yeah, today I want to talk about mapping the universe using galaxies and how can we learn physics using maps like this. So let me begin from the beginning, which actually begins with a bang. It's not a very loud bang, but it's a bang everywhere. But we don't really understand much about that. But just to bring everyone in sort of the same framework, how we are thinking about universe, after this initial phase where pretty much everything begins and we don't really understand what happens, we think that universe went through this rapid expansion, which is called inflation. And then that expansion stopped at some point. And at this point, universe was highly coupled plasma. And so all of these things we can actually propose and set up the equations for that, but we can't really see directly. And so beyond this comes to a phase, which is the observable universe. And this is where we can actually observe things and then try to infer things beyond the observed universe, as well as what's happening within the observed universe. So within the observed universe, the first images we have seen is cosmic microwave background, and I'm sure you have heard many talks about cosmic microwave background. So this is where the first time photon decouples with the plasma in the early universe and free to flow. So free to fly and come to us and come to our telescope when we put them exactly at that time. So beyond CMB, there was pretty much nothing in the universe to begin with, in the sense that there were not a lot of activities. It was pretty sort of sterile and cold environment. And then things happened, and I'm not going to talk about anything in this era, which is called dark ages. And there's a lot of work going on. And it's one of the exciting frontier of cosmology called cosmic dawn. And people here at TIFR, as well as all over the world, working on it. There are many major missions focusing on that. But beyond the dark ages, then comes to the part of the universe which we are mapping by looking at the galaxies and the optical lights in those galaxies. So that's the later part, which is the 10 billion light years of the 10 giga years of the universe from now. And that's what I'll be focusing most of this talk about. So what you see in this observed universe is these red points. These are galaxies with supermassive black hole. And they are very active. So these black holes are doing a lot of things. They're accreting material and they're emitting a lot of light, which is why we can see them. And then in more nearby universe, these are more traditional or typical galaxies, which are shown in yellow point. Now you'll ask why all the black holes are living in this part of the universe and why there are none here. That's basically observational bias. So as you look far away from us, you need to have brighter object to actually detect in the same size of a telescope. So if you want to detect a dimmer object, you need to make your telescope bigger. And so what happens is that these objects are, although very rare, they are very bright. And so we can see them to far away distances. But when you come to nearby universe, we can see them, but they are rare. So you don't see them enough. So there are few red points, but there are not many, right? But we can see these dimmer galaxies, which we cannot see to very far away distances. And so all you're seeing is a sort of observational effect. There are also some galaxy evolution physics there, which I'm not going to talk about, but happy to address if somebody have question about. So given now we understand like what is the baseline of the observable universe and what is the picture we are working on, we can sort of get going. So I'll give you the result upfront, and I think all of us have seen this in several talks, that by analyzing these detailed maps and all these data, what we have learned overall, the major sort of understanding of the universe is that there are mainly three components. The first is baryon, which is what we expected to exist all over the universe when we started this journey, but then we figure out there's something called dark matter, which makes 26% of the content. And then we also figure out there's something called dark energy, which is causing accelerated expansion of the universe, which is 69%. And we have very precise measurement of this. So these are not percent level precision. We have measured these quantities. So far, Einstein GR works pretty well to describe most of the broad level things. There are tiny details which we are sort of struggling with and trying to figure out in more in better way. We also have a constraint on curvature of the universe, which is more or less flat up to 3 decimal places. There might be curvature below that level, and we'll know in next 5 years. We also have a very good understanding of the fact that this dark matter interact gravitationally. So if you leave this along in the universe with perturbations, then these perturbations are going to grow, and they are going to be varialized and collapse objects, which are called dark matter halo. And this is exactly what provides the house or the right environment for everything else to form. So if there was no dark matter halo, no galaxies would have formed, no stellar system would have evolved, and probably no living being. So it's very essential, given it's such a massive component, it's a very essential part of how the structure grows. So now coming back to what exactly I personally do, focus more on that. So we basically what we do is we analyze these sort of maps, which is actually a movie flying through, looking at different galaxies, and you can see that they're located in three-dimensional space. So we're flying through that. These are fairly local galaxy, and this movie is already 10 years old. So we have far superior maps than that, but this is a nice illustration to show that. And each point you're seeing here is a galaxy. And so to be able to make this map, it's difficult. The reason being that what you need to understand is you need to localize them in the sky. So that's the 2D position, but you also need to figure out how far these objects are. And I will show you later some images which will make it clear. We also need to understand what kind of object these are. And so those additional information require collecting a spectrum of these galaxies. And spectrum is an expensive process. Anyone who worked with a spectrum would know that how difficult it is to collect a spectrum. So you have to collect the light from the particular source through a fiber, pass it through a prism, spread it over wavelength, and then record it, and do all of this without introducing lots of noise and biases and things like that. So yeah, that's a very expensive process to actually make maps of this. But then what does it really mean to analyze these kind of maps? So at the bottom, what we are really trying to do is we're trying to follow photons as it's emitted through various physical processes, and then follow it all along its path, all along its journey from where it's emitted to us. And it experiences several physical effects when it goes through this journey. So understanding, first of all, these physical effects, modeling them theoretically, and then figuring out and then putting that all together when we look at the data is exactly what we are trying to do. So when you see, for example, when you saw that green TIFR logo, whether it's really green, it's not a physical object, so it's not a good analogy. But actually, the color I wanted to put is not blue, but green. But it appeared blue. So there's a effect through a projector which made it blue. So similarly, when you see these objects, so these are globular cluster, and it's an image from Hubble, and you see lots of different color. But these are not the true color which these objects are emitting. The true color is something slightly different, and it has gone through some physical process. If we can understand and model that physical process, we can learn about the universe. So that's the sort of really the crux of the things we are trying to do. We're trying to understand what all different kind of effects a photon can experience and model that and understand what the content of the universe looks like. Okay. Right. So now let's get a bit more sort of specific about these effects. And so there are many such very interesting effects. I'll focus on only 2 or 3 of them. And so the first one is if you emit a light from any star, right? For example, in this particular cartoon, sun is shown here as an example, and of course it's an exaggerated image. As the photon, if it's a monochromatic photon with a particular wavelength, the wavelength of the photon as it travels away from the sun, it's going to change. And the reason it's going to change is because it has to climb out of the potential well of the sun. So it's going to affect the energy of the photon, and this is what is called gravitational redshift. So that's one particular effect which we are actually trying to detect in the large maps of these galaxy survey. It hasn't been detected yet at high confidence. We have evidence of these things. We have like 2 to 3 sigma level evidence. We think we will be able to detect effects like that coming from galaxies due to the existence of this dark matter halo with like really high significance, 5 or 10 sigma significance in next few years. But then if you think about now a galaxy, as I mentioned, these galaxies are living in their home, and these homes are dark matter halo. So this massive density region around them, which is a lot of matter, and that provides a very, very big potential well. So it has to climb the potential well of the dark matter halo, and so you'll see a shift in the photon wavelength. And as it climbs out of that potential well, then it is traveling through the free space. Now in this free space, we expect that is going through the free space, as it travels, the space itself in the universe is caused by dark energy, sourced by dark energy, and so it's going to again expand. So it's going to again get shifted. And so what this allows you to do is, if you can measure the wavelength of these lights, and if you know what is the expected emitted wavelength, is, for example, if you know a particular atomic or molecular lines and you can see them, and if you see them at shifted location, you know how much of the shift is. But you can't separate them individually, but that allows you to actually at least measure these shifts. And this is what is called redshift, the total shift. Yes. Yeah, so this is highly exaggerated version. You'll not see that. The part of dark energy will not be highly exaggerated as you go to further away from us. So as you go to larger and larger distances. So but yeah, all these are highly exaggerated.
So in terms of, let's say, frequency or wavelength, what is the shift you expect because of gravity?
So in terms of wavelength, this is a function of how far the object is. And so you can basically say that delta lambda over lambda is essentially 1 plus z.
So you are looking in what wavelength regime are you visible, or? These
are all optical. So we are all so within the optical, we are talking about the shifts. So shifts can be of the order of I think 10 to 100 nanometer, depending on how far you are looking at objects. So it will be a function of redshift.
So the fact that you don't have a more than a 3 sigma detection is because of spectral resolution or some other issue?
No. So that's a different thing. When I said we don't have a more than 3 sigma detection, that's about the gravitational redshift itself, right? So we see this shift in pretty much all galaxy spectrum, and that's how we measure distances. But the shift because of the expansion and because of the distance is actually the dominating. If that's order 1, then this shift is order 1 over 100, this effect. And you can't separate them.
Okay.
So individually, actually detecting just the effect of gravitational shift is hard. That's why we haven't seen that.
Good. Thank you.
And so there are also effects which is of order 1000, which I'm not talking about beyond that. And then hopefully at some point we'll see those effects as well. Right. So so this is what we are trying to do. We are trying to make maps. We are trying to make these maps as a function of wavelength. And so we are collecting a spectra of a large number of galaxies and trying to model all the physical effects on the way of the path of the photon. And then we want to address several questions about the universe. And so there are many sort of big questions I will just put here for the broader audience, for a broader set of questions. Things like how did universe begin, to what is the nature versus nurture of galaxies in the cosmic web. And so this is particularly something I really care about. And just to sort of expand that a little bit, what we are really thinking about, as in, if you think about a human being, when he's born with a genetics, and genetics actually determine a lot of features of a human being. Right, but then it grows in different environment, whether it's in a city or in a colony or it's in TIFR or ISC, and all that actually nurture this human being, and that also affects. Now it's very hard to disentangle what part is because of the nurture and what part is genetics. And so you can actually try to do a statistical study of this kind and figure out how much is nurture is important, how much is nature is important. These days, when we are, I'm a parent, so when we try to do parenting, we think everything is nurture, but many times things doesn't work out that way. So similar thing you can ask about galaxies. So they born with some particular genetics, in the sense that they born in a particular locations in the universe, and now they are growing. But then they are going into different kind of dark matter environment, different kind of other dark matter halos. How much of this larger scale environment matters versus where exactly what kind of content it's born with, it matters. And this is going to play a fundamental role when you're trying to understand cosmology through this survey. So often this is called astrophysics or galaxy physics systematics in cosmology language when you're thinking about cosmology. But if you are interested in understanding galaxy evolution, then that's one of the fundamental questions you want to address. So the genetics is probably, for example, if a galaxy is born in some region where a particular kind of supernova happened, there's a particular content of the metal and things like that, which is what it's born with. Right? So initial mass function and things like that are the genetics, and then whatever environment it's born in is the nurture. So So with that, let me give you a few examples of how do we approach this problem. So rather than giving you a very big picture, I want to give you a little bit about idea about how do we really approach a problem. So let me talk about a very specific problem. So yes. Yes. No, so then you have to. So galaxies are basically a collection of stars in some sense, right? So this collection of stars is going to affect the collection of stars it's born in and the star its neighborhood. So of course there is no direct something as specific as gene in the galaxy evolution language, but this is just an analogy to give you some idea of that there is a local effect. There's basically something very local and there's something slightly global. And so how does those two things affects that? Other thing you can think about in terms of galaxy when you're thinking about analogy of genetics, when is it born? In what time of the universe does that affect? And so the evolutionary pathway and the surrounding is going to get affected with that. So let me go to a specific example. And I guess many of you have seen this particular press release, and it was all over the news that we have finally seen the black hole at the center of supermassive black hole at the center of Sagittarius A star. And people have been observing and measuring these the regions around this black hole where we are seeing these stars are going around, and have measured this movement of this star and also already estimated the masses of these black holes over the last decades and so last couple of decades. But finally, we were able to measure this image. The reason this making this image was very hard is because it's a very tiny thing on the sky, and so you really need a very good resolution. And so you needed a telescope of the size of the Earth is what required. Now, these kind of supermassive black hole we think is at the center of every galaxy. But there are certain kind of galaxies which, if you look at the supermassive black hole around them, they are actually dominating the whole galaxy. So the light emitted from the whole galaxy is dominated by the central region. So things around the central region, which is called disk. And so these are called active black holes or active galactic nuclei. There are several terms and they are slightly different, like AGN or quasars. And so one of the question I wanted to address is that why does it happen that some galaxies have this active black hole and some do not, although all have supermassive black hole according to our understanding. And so you can try to now think about this map picture I've been trying to build up here. So what we are thinking here is that this dark matter halo is essentially like a colony, right? And these galaxies are like buildings, or maybe you can think about this dark matter halo is like a building, and then these galaxies are different apartments. Now, there are different kind of galaxies that I've divided into three categories, but it's sort of a continuum. Now, you want to ask, like, why do these galaxies have active supermassive black hole, but this one doesn't have active supermassive black hole? And so what kind of physical process dominates this kind of effects? And also another question related to this is, like, if there's a galaxy here, the nature or the thing about this galaxy, properties of this galaxy, does it get affected by what is the neighboring galaxy? So this is again getting into that nurture part. So there's a star-forming galaxy here, and next to it there's an active supermassive black hole. Will that actually affect this particular galaxy?
Shadab,
yes.
Could you just quickly tell us, for the people who are absolutely outside, what is the difference between active galactic nuclei, means active black holes versus...
Right. So all of these galaxies have a supermassive black hole at its center, but some of these black holes are so active that they have an accretion disk around it and they are emitting a lot of light. So basically the dominant light coming from that is coming from that region around that supermassive black hole.
Okay.
And often they are seen with these jets.
For the other black holes,
for other,
you don't see that. You don't
see that. Further, you see the rest of the stars in the galaxies, and so you see the whole galaxy rather than that central region.
Okay.
So that is the difference. And so why does this become active? Right. And so
now we know that in the cosmic neighborhood is around 10% galaxies are active, roughly, right?
Mm-hmm.
Whereas as you go back, well, you already mentioned that we only see them, so you don't know real number. But in the kind of simulations, can we kind of estimate whether those fractions were evolving over the time?
Right. So in simulation, we can. In simulation gives you reasonably precise prediction. The only difficulty with simulation is that given these are rare objects, to actually map the rare object nicely, you need larger volume. So if something is only 3% of the fraction, and if you have like say, let's say only 100 objects in your simulation, there are only 3 of those which are of that kind. And so you need bigger and bigger volume to actually map that very well. But simulation does give this answer, how the active fraction changes as a function of redshift or epoch. In data, so that's in fact one of the critical. The thing I'm going to show you is only feasible because now there are data where we have these different kind of galaxies in the same epoch mapped, and this was not possible earlier. What I'm going to show just now. So yeah, sure.
There's one comment on the simulation aspect. So the feedback processes in the simulation varies, as you know, like orders of magnitude depending upon who is doing the feedback, whether it's an instantaneous process or slow shots. Both changes the results of this kind of galaxies tremendously. So I think we are still improving the frontier of simulations, even for small
Right. So the fact that fundamentally we do not know why exactly this gets activated, in simulation we have some mechanism to get them activated, or it's not exactly that mechanism, but some prescription to get it activated, and those prescription varies simulation to simulation, and hence the result varies simulation to simulation. That's why it's also even more important to sort of get a direction from data itself. Right. So let's say I want to address this question. How do I go about it? Let's say you go out and look at the night sky with your eye. You can, if you go out in Mumbai, you'll probably not see anything at all. You'll see a few stars. If you go to something like Ladakh, you'll see many stars with your naked eye. And so your naked eye is not good enough to do this kind of thing. So you want to build a telescope. If you're able to build a 4-meter optical telescope, you'll see something like this. So this is an image from 4-meter optical telescope, but it's not one image, it's stacked several images from a 4-meter optical telescope, and that's the moon for a scale for you. But when you see this image, you don't really see this kind of thing, right? So you see some small blobs, and with the bad projector, not so good projector, you see even like worse. So this projector is actually doing something what our atmosphere do, which is effect of seeing. Right. So what you need to do is you need to actually go ahead and do somewhat more detailed measurement of these things, and basically take a spectra. So this is something I mentioned before. So if you now start taking a spectra of these individual galaxies, you'll see as a function of wavelength, you'll see various different features, various different lines you can identify. So for example, in this particular image, this is for one of the active galaxy, you see Lyman alpha, carbon 4, C3, Mg2. And since we know the expected location of these lines, we can actually now measure redshifts of these objects. But also the detailed features of these spectrum allows us to infer what sort of a star formation is going on. So what's the star formation rate? So it's a star forming galaxy or non-star forming galaxy, or it's an active galaxy. So you have to go and not just take an image, but also take a spectra of all of that. And let's say if we do that, then you can generate maps like this. So it's basically a refined version of the same map, but now I have assigned the galaxy type for each of these things based on the spectra. And you can also create a map of dark matter, underlying dark matter, with some proxy there. So there's some theoretical assumption, which I'm not going into, but you can actually create a map of dark matter itself in that particular region once you know this information. So now you have 3-dimensional distribution of these galaxies, along with galaxy type, as well as some estimates of dark matter. So now let's say one of the proposal is that these galaxy, so one thing, yes?
Just a map of your redshift.
So it's both redshift as well as the sky positions that gives you a 3-dimensional map.
Yeah, right. But it's a map of the redshift.
It's map of 3-dimensional map of galaxy. I'm not sure what you mean by map of redshift.
What is the dark matter component?
What is the dark matter thing? Yeah, so now you have 3-dimensional map of the redshift. So what you can do is you can say that galaxies are following dark matter. So that's the assumption which I mentioned, which I was going to skip. And so you can say that galaxies are biased tracer of dark matter. So using that, you can estimate what is the density of galaxies, and if we can measure bias as well. So what is the bias amplitude? Then you can divide that bias out and get the map of dark matter itself. Does that make sense?
No.
So we are saying that linearly the number of galaxy in a particular part of the space is proportional to the dark matter density. That's the assumption we have. So this is linear theory.
Okay, and that's all. There's no
other thing. Yeah. And so this works when you look at the when you smooth things to large enough scales. When you look at the close enough, it fails.
So Shadab, the reference line, so suppose you take iodine, there is a transition, you are measuring it on Earth, right?
Mm-hmm.
So are you assuming that here there is no dark matter? I mean, how do you know that what you are measuring is actually your reference is correct? Right?
What is a reference?
Like it is reference to
even if this dark matter, it's not going to do anything with the line you measure, right?
But you are saying that everything gets redshift.
So everything gets redshifted when you start traveling. So when you start moving away from something, right? So if there's a gravitational potential which you are living in, and a photon tries to come out of that gravitational potential, then things get redshifted. If it starts to travel in the free space, then the dark energy is going to start redshifting.
But photon is always traveling. So in the Earth's field also, it's always traveling.
Yes. So in principle, the instrument itself, let's say you have an instrument which is emitting this photon, and you have a measurement device here. Now, if there is a gravitational potential difference between these two places, that redshift is going to be seen. But that redshift is going to be very small, negligible, which will not detect in your instrument.
And suppose
so it's a function of mass contained in that sphere.
So suppose outside 100 kilometers from Earth there is some dark matter. Suppose, and it is not going to affect what I measure here as a
no. So is the Gauss's law will percolate, right? So it's the relative shift in the enclosed sphere, imaginary sphere you're going to draw from the point it's emitted to a point it's observed. So it's really the mass enclosed is going to affect the potential in that space. So it's the potential difference. It's a difference in potential.
What if I measure something here and here? Is the transition?
So that is that's the height. So in fact, there is a measurement of that. In Oxford, there was an experiment to measure gravitational redshift for the first time. What they did is they drilled hole. So they had a detector at the bottom of the building, and it was, I think, 3-floor building, and they dig a hole in the two of the terrace, and then they had a detector on the top. And now they have emitting sort of a macron wavelength or something, which a photon is emitted and then bounced back. And this is a very difficult measurement because the effect is going to be very small. But if you devise your instrument such that it can cancel all the noises, which is basically you shift the wavelength of absorption and emission such that it's exactly matches, and you keep shifting till you match, it's sensitive to very finite length of wavelength, you can detect this. And this has been detected. There was a experiment called Pond and Rebecca in 1964 or something, which have detected this measurement. So you have that. Right. So there are 3% of these things which are active in this map. Now, let's say if I want to try to look at this quantity where I have drawn a dark matter density, which is again coming from this proxy, which has these assumptions which Sorindo asked about. And if I just look at very simple quantity, which is the fraction of red galaxy as a function of this hypothesized dark matter density, what you'll see is that it's a positive slope. It will increase with a dark matter density. If you try to ask the same question for these blue galaxies, what you'll see is the inverted relation. And this all can be explained based on our understanding of this galaxy formation. Now, the main question I wanted to ask about is this active galaxies, right? So if you'll ask about these active galaxies, what do you expect? So depending on what model you propose, let's say you propose a model that every time two galaxies merges, the black hole merges and there's some vigorous event, and that's what makes the merged black hole active. Then it should follow the merger rate as a function of dark matter, and that merger rate is going to follow the dark matter density itself. So you should see a positive slope in something like that. But let's say I'll make a statement that at the scale I'm looking at some smooth scale. None of the physics is going to actually matter at those scales. All the physics which is operating to make this active is very close to the black hole scale itself. And so it should be as good as random distribution. So there should not be any dependence in that case, right? So we can actually measure this, and the result we got is more or less flat with a very slight tilt. And so things like this merger scenario is not the main driver of making these galaxies active. So you rule out one scenario being the dominant effect at these epochs. So we can sort of similarly continue addressing that for you.
Just I have for the halo, right?
Mm-hmm.
It's the halo.
Can I use this as a proxy for, active galactic nuclei versus active galaxies versus the normal? I'm going for the disturb. I know it may not be possible to kind of map this
Right.
down.
So no, in fact, we do have a program, and I had a summer project of 10 students looking at something like this, which is actually finding all the dark matter halos in our local universe. These are called group scale halos. And so just finding the dark matter halo itself is a challenging task, but we can do that. There are algorithms to do that under certain regime. And then once you find that, you can look at these kind of statistics for that. But right now, we don't have enough statistics to make a statement about whether that is the case or not. But hopefully, that is something we can do in the future by looking at the dark matter halo in our local neighborhood and see what kind of feature we see. Yeah. Right. So this is a more technical plot of the same thing I showed you in a cartoonish version, where these black points shows the measurement, and the colored line shows this model, which is essentially saying that the black hole doesn't care about at the smoothing scale we are working with. It doesn't any physics involved is not important, and so whatever the physics is at a scale smaller than this, so we have to refine our map better, and that model more or less predict goes through the data point. And so this is sort of the kind of approach we take to slowly refine these sort of questions about what is really playing a role in making these things active. Another aspect is that since these are, I told you that, dark matter halo is the building in which galaxies are living in different apartments. There is always a central apartment, the most important apartment, which is at the center, because it's a spherical object which is at the center of the dark matter halo, center of the building, which probably everyone want to live in or everyone want to avoid. And so we have this idea of whether the galaxy, this active galaxy, is always at the center or not, is another question we wanted to ask. And what we found is that based on this modeling, which I just described, that at least 20% of these has to be not at the center. And so this doesn't happen only at the center of the dark matter halo. So that's not, again, it's not a special condition when these galaxies become active. Okay, so this sometimes works, sometimes it doesn't work.
The similar argument says that things are expected
to the center by dynamical friction. So the mergers, that's the kind of argument. You're saying that roughly 1/5 of those are not really related to that kind. Okay.
Yes.
That makes sense. Thanks.
I said 20%.
20%, not at least 20%.
No. So 20% with the error bar. I didn't mention an error bar, but yeah, 20% is the mean value. I don't remember the error bar, but it's probably plus minus 10% level. Right. So let me give you another example of how we sort of try to address some fundamental question by looking at this sort of map. So this example is about testing gravity, let's say GR. And it's slightly more simplified for technically minded people. So please excuse me for that. So we are looking at essentially trying to figure out a very simple, what is the force law between a pair of objects. And let's say there's a constant of gravity, G Newton constant. And what I want to ask is, can I measure this G on cosmological scale? So by looking at this map. So we can measure this G on Earth or in our solar system. These are very precise measurement. So with an error of 0.002%. But we can measure this same G by looking at this galaxy map and by trying to observe the dynamics of it. I will tell you how we do that. But just to give you the question is really, is the G universe everywhere else in the universe is same as on Earth? And why do we care about? So my reason to actually do this is because, our GPS system will work everywhere. We don't need to measure G as a function of where we go, and our navigation will be smooth, right? So if G is same everywhere. So what we have found is that through various experiments, that within 5%, which is our uncertainty measurement, compared to this 0.002%, at cosmological scale, within 5%, everything is consistent with what we measure G on Earth. But then how do we really do that? So let's try to develop some intuition about this. So if you were to go again and fly away from Earth, far away, such that you can see the structure, cosmic structure around the Earth, where Earth is at the center, and this is the angle in as a RA, so as you move along, and then you say take some slice along deck, some narrow slice, 5-degree slice along deck, and plot each of the galaxy you see as a one black dot. So this is what this map is showing. So it's essentially showing the structure of galaxies around Earth in some narrow declination band and as a function of RA. So it's just trying to show the three-dimensional structure around us, right? And so this is what you'd expect, and this is actually a simulation, not a real data, but we can make similar images with real data now. But we don't see the structure of what I showed you in the previous slide. We should see something like this. And so there's some difference between these two. So what you see is that these structures are elongated along the line of sight. So if observation is done from Earth, then these structures are elongated along the line of sight. So that's what you're seeing. And so the physics of this elongation is what will help you measure G, and what we use to measure something like this. So let's try to get to that physics. You have a telescope which have lots of spectrograph, and a galaxy is emitting a light. You're trying to measure this spectrum where you want to figure out certain lines and look at the shifts. And so you'll finally measure a redshift, observed redshift. So this observed redshift will be a function of cosmological redshift. So this is the redshift because of the expansion as it travels through the free space. But these galaxies are not somewhat dull and boring like us, like a scientific institute. They have party all the time. They celebrate Durga Puja all the time. So they are dancing. They are actually very interacting with each other. So they have large velocities around each other. They are going around. And so because of this velocity, what's going to happen is that there's going to be additional Doppler shift on top of other effects I talked about. And this velocity component is only the line of sight component. So only if a galaxy is dancing along the line of sight, any component in the line of sight, that's what is going to get affected. Everything else is something you're not sensitive to because it's perpendicular effect, right? So in terms of Doppler shift. So that kind of effect is also going to get added to your observed redshift. Now, if you look at a pair of galaxy in the sky, like is drawn here, they might be doing whatever, but they are interacting gravitationally. So on an average, if you look at it, there will be a net force towards each other between them. Although there might be other additional force because they are living in this environment. And because of this attractive interaction between them, there's going to be a velocity towards them. So this is what we call large-scale infall. This large-scale infall is what we want to see and what we want to measure. So how do you actually extract it? So I told you that it's going to be there in each individual redshift, but how do you extract that information? How do you sort of see that? And so that brings me to the idea of two-point correlation function. So what we want to do here now is that we want to take our map and we want to sit on each galaxy one at a time, and then ask around me if I scan, and I always want to define a special direction, which is the line of sight. So Earth is at a special place. So you should remember where the Earth is in whichever galaxy you are living in, right? Because we are important. So you want to define a special direction, which is the line of sight viewed from Earth. And if I look around and look at the distances of all the galaxies around me, perpendicular to the line of sight and parallel to the line of sight, and I just count how many galaxies I find as a function of distance, and I go and do that on all galaxies, sit on all galaxies and do that. This is more or less, this is what is two-point correlation function. This is a slightly more subtle thing, which I'm going to again skip unless somebody asks. And so if you take a map of something like that, if you create a map like that, in an isotropic universe where there is no velocities, if galaxies didn't have any velocity and our redshift didn't get affected, you'll see a circle here, basically isocontour, because all directions are same. We are not important. But we are important because the velocity component of the galaxies we are sensitive to. So now what happens is at large scale, these galaxies appear closer than it actually are because of these velocities. And so in place of a circle, you see ellipses. So if you draw contour again, you see that there's a missing region. These are actually very green region because projector doesn't have any green. So it's just a feature of you're seeing artificial rings there. Don't focus on the rings, just focus on the overall shape. Okay. If you can measure this ellipticity, we can calculate what that ellipticity correspond to given, like, let's say you propose a Newton constant, you can calculate how the ellipticity should change given everything else. And so by measuring quantities like this from galaxy maps, we can measure. And so at this point, actually, I can go home and I can finish the talk. But unfortunately, the real surveys do not look like the simple ellipse I showed you if I measure this kind of quantity. It has something like Sauron's eye, so something very strange at the center. And this is, in fact, what you were seeing in the first image I showed you between the two versions of the cosmic web. The things are elongated. So what is this at the center? And this is a nightmare for us. I mean, this is actually a nightmare, and this is also why I'm in this job. Otherwise, I don't have to be there. We already know how to model the first part, and we just have to make this map, and we are done. So what is this thing at the center? So that thing at the center is basically doesn't change. So that thing at the center is basically very nonlinear physics and very messy physics, which is very hard to model. One of the way to do it is do it through simulation. So what happens is that since we are living in a building, all these galaxies are living in a dark matter halo, they are interacting. Now, why don't they fall to the center? Because they're living in this gravitational potential. If I leave you at certain point from the Earth, you're just going to fall to the Earth, right? The only reason you won't fall to the Earth if you are a satellite which has a tangential velocity such that you go around rather than falling. That's the only way. Otherwise, you'll fall to the Earth's gravity at the center. The same thing should happen to the dark matter halo, which means they have actually a lot of varial motion and velocities. And now this same velocity is going to affect your redshift. These velocities are much larger than this large scale flow I was talking about, which are smooth. So these velocities should be enough to not fall in the center. So you are going around in some orbits in this dark matter halo potential. And because of this large velocity, what you see is this elongated structure. So I have extracted you. So this sort of image is only possible to make in last couple of years. Otherwise, we didn't have the tools, theoretical tools to do that. Now, what I'm showing you is just this nonlinear physics part of the problem. But in the data, you can't separate these two things. In the data, you get the full thing, and you have to model both of them together. Right. So once you combine this, and so one of the challenge, like really the frontier in large-scale structure analysis, is figuring out where this nonlinear effect is important and where it is not, because that is what is going to allow you to measure parameters in an unbiased way or in a controlled way where your theory systematic is controlled. And so one of the things we want to understand is that where this transition happens, where, given the precision of the data, whether I can model this effect sufficiently good enough or not. Yes.
In the perpendicular direction, the perpendicular line of sight, why do you still see a spread? And I understand the spread is mostly in the parallel.
Yeah, so that's again a very interesting question. The reason you see this spread is because you will have this dark matter halo of different sizes, and you have galaxies of different magnitudes, so they are living in all different sizes. And so what's going to happen is that a smaller dark matter halo will only appear up to a certain scale, but a bigger dark matter halo will appear at bigger scale. And these are not entirely restricted to just within the what we call varial radius of the halo. There's going to affect slightly beyond that. But there are mixture of scale. There are mixture of these buildings, and so there are mixture of these scales, mixture of halo, which is what shows this spread. And so depending on what kind of galaxy sample you're looking at, this spread will look different. I will in fact show you when such things, but I should rush a little bit. Right. So is our picture. So now I can go home. We just have to address this challenge, but there's actually something more interesting going on here. So I gave you this picture already, right? And so I talked about what you can do with this map. I told you that this is already very precisely measured. We have percent level measurement of this cosmological quantity. But then the photons travel. I told you that we want to model path of the photon, right? So when the photon travels from the CMB, it comes through all this structure. And so they must be doing something more than what I just told you. And that's essentially what is called gravitational lensing. So when the photon from CMB or anything in the background comes through all this structure of dark matter, halo, and galaxy, it bends. Of course, these bending are exaggeration. These bendings are very small and very tiny in the real universe, and so it bends through this, and we can actually take out this bending pattern, or the photons are bending, by looking at this CMB map and galaxy together. So this is called CMB galaxy cross correlation or lensing, and this is another way to extract information about cosmological structure as a function of epoch of the universe. And so let's say now I want to put, somebody want me to go home, I think. Okay, so let me just go over this very quickly. So, what we want to measure in a sense that how much matter is there. So that's on the x-axis, and how smooth is this distribution. Whether the road is bumpy like this, so very non-smooth, or whether the road is really smooth. So that's, we are talking about the dark matter distribution itself. And the CMB gives you very precise measurement, which is somewhere here. And if you try to measure this with something like CMB lensing, you get a curve like this. And so this means basically our universe should be somewhere in between these two red lines, right? And this two red lines doesn't pass through this point, and so we are missing our universe somewhere in between, right? So if it's consistent, if it's the same universe, this two red lines should pass through this green point, but that's not the case. And so this has been pointed out already, I think around 4 to 5 years ago, but it was very feeble signal. But there are several analyses now, including us, who have shown that this actually exists. We don't know where is it coming from. Either there are two different, there is some sort of systematic, there is something we're missing in terms of the physics followed on the photon path. Yeah, so the inconsistency between this and that is about like if I project it into some space like that, I can look it into one dimension, one parameter, right, which is the most deciding thing, and then you're at the 2.5 sigma. This is already 2 years old. Now we have like almost 3.5 to 4 sigma from newer analysis. Okay, so this is a more technical version of the same plot, but then I wanted to show this plot, which is actually more recent, where what we are saying is that I told you about this nurture. Now, what I want to show is that this is the CMB, and this is one measurement in which I'm saying that galaxies are like TIFR building apartment, which means we don't have the choice of where to live in terms of particularly who our neighbors are given our allocation system, right? But if you are in a private housing, you can choose, you have more freedom. So if they are actually, they can care about what the neighbors are and things like that. So we have developed a tidal field model for that. These constraint shifts. And so it's very...
What does that actually mean?
What does it actually mean? It means that when I'm talking about these galaxies in this dark matter halo, they don't only care about the mass of the dark matter halo, they also care about what is the tidal environment. And so what is the tidal environment, tidal field? And so depending on what kind of tidal field is, different kind of galaxy will be more or less likely to live. And if I do that, and I have another way to constrain, let's say, the tidal field correlation, then that will affect my constraint.
What is the length scale over which it's detected?
So these are at length scales of 5 megaparsec is what we are working with in this case. So this is much bigger than galaxy and halo scale.
So why would something at that length scale determine the kind of galaxies that there are? The galaxy, the length scale for the galaxies is much smaller, right?
Right. So that's a good question, and we don't know a particular physical reason, but what we have found is the evidence for that in data. And the reason we think it matters is because although the galaxy itself is much smaller, the material it has access to. So the way it grows is by eating material,
IgM.
right? IgM and then things around that. That is coming from all the surrounding area, and the exact pathway is not known. But we are hypothesizing that it matters. And if it does matter, we do see strong signature, then we need to dig deeper to see why, like what kind of processes are dominating that.
When you say which kind of galaxy, is that just a matter of chemical composition or?
Star formation. I'm all talking about it's mostly star formation rate. So whether it's a highly star forming galaxy or non-star forming galaxies. Okay. So I guess I can rush through this part. This is about the future, so there's no new result here. So yeah, you can do this sort of exciting science, and I hope I conveyed some of the approaches to answer this question. So that was the main goal here. But then there are lots coming up. So there's a survey called DESI, which is the main thing I want to highlight is that in 5 years, it's going to measure 40 million spectra. This is the focal plane of DESI, which has 5,000 fiber, versus this survey, which is SDSS, which measured 2.5 million spectra in 20 years. Simply because you had to plug those fibers, a human had to plug those fiber at the location of each galaxy each night, drill a hole and plug those fiber. And that takes time, versus now we have robotic fibers. So that gives you this scale up. So this is already ongoing, and we are going to have like really massive map for this. And so we can refine our map much better, and all the problems I showed you can be addressed in much more detail. And so this is something I promised earlier. Now this is the same thing what I showed you, the 2-point correlation function showing redshift space distortion, but in real universe. So this is measurement from 1 month of data from DESI. So with SDSS, even with 5 years of data, you could not have done this kind of measurement. And so what you're seeing here is at the function of epoch, so 3.5 gigayear, 6.8 gigayear to 9.3 gigayear, you're looking at different kind of galaxy, and you're trying to look at the same pattern. And so what you expect is that there are two things here. One is what is this nature of these galaxies themselves, right? So where do they live in, what kind of building or what kind of dark matter do they live in? Other is the cosmology. So you should see the cosmological evolution, what is the peculiar velocity flow as a function of epoch. And so both of those two things you can disentangle by looking at this map and analyzing them in more greater detail. See, this is not sigma tension. This is just a 2-point correlation function as a function of cosmic evolution. And you can extract sigma information using this. So this is real data. Right. So many more large-scale structures are coming in next 10 years. In the interest of time, let me not go into the detail. I'll just show you one more survey, which is called Foremost. This is going to be like really nice local universe survey. So it's really focused on below redshift 0.15. So really local universe. And going to what's most unique is that it's going to observe 20,000 square degree in the southern galactic cap, which is largely unobserved so far. So for some reason, we have more telescopes in the northern galactic cap. So we know northern part of our universe much better than the southern part so far. But that's going to change, especially in the spectroscopic regime. So spectral resolution, I think it's R of 5,000 in the optical range. But they have 3 different type of spectral resolution. The highest resolution is much better than 5,000. Lowest resolution is worse. Right. So yeah, this brings me to my sort of one slide before conclusion slide. So what do we expect, just to share the excitement? What do we expect? We expect if we were to do this survey and do these measurements, so I talked about, we'll be able to measure this mysterious component dark energy, whether it evolves with redshift or not, to 1% precision. Right. And so we hope to find new angles in dark energy physics with something like that. We'll measure neutrino mass. This is something I didn't talk about, but there is this particle called neutrino. There are 3 different kind of them in the standard model, and we know their mass difference of these 3 very well, but we don't know the relative order, and we don't know the total mass. And so that is something cosmology is going to give you, the sum of neutrino mass to 0.02 electron volt. We will measure this Newton constant I told you, essentially through redshift space distortion much more precisely. So right now it's 5%, it's going to be 0.6% level in next 5 years. Then there is something, again, I didn't talk about in the beginning of the universe in my picture, right? So what was really the conditions where, right? What was the initial condition of the universe look like? Where there's some special feature where it was mostly Gaussian. So there are some special features which we look for, which are theoretically motivated, and we are going to improve the constraint on that in the near future. So yeah, with that, I'll stop with this slide for end talk.
Thank you very much, Shadab. The talk is again open for questions, and I'll pass on the mic. Let's go.
Very nice talk, Shadab. Question about the G. I have not been following up that precise measurements. I thought step was cancelled. That was this equivalence principle test that's supposed to measure G up to 1 part in 1,000 or maybe better. So you kind of put a local measurement of G, in one of your slides.
Mhm. I don't know much about the local measurement, though, although I put
Yeah,
it for
that's what I was
comparison.
a bit confused about that. I mean, so
So this is
that,
not cosmological.
no. So I'm not interested in the solar system measurement. I'm talking about the actual measurement of G. If I'm not, I may be wrong, but those were not obtained that accurately. I mean, you can create a combination, but that's not what I'm interested. So you pointed out some G to be 1 part in, I don't know. I think the
Yeah,
error bars were very
2 part in 1,000, I think.
So that's right.
Yeah, so those are, I think, these
Is
the
it
satellite missions is what
Okay.
measures this.
Because the STEP is not funded.
I don't know exactly which mission measured this, but this is what the quoted error I
I
found
should
in
look
literature.
into, yeah. So satellite in the sense of between planetary explorations, or that's
Yeah, I think these are from planetary
That's 20
exploration.
parts in a million.
Yeah, so it's
that is problematic, because I know that G itself measurements like the torsion balance and better than that, those are very bad. So this is some combination.
I think these are probably these planetary.
Yeah. So then they come with the masses, and that's not a pure measurement. So
yes, it's not like a tabletop experiment.
yes,
for
so
sure.
which you actually, so that's the reason I was surprised that, because STEP is supposed to, this is called Satellite Test for Equivalence Principle. That is not funded, to best of my knowledge. I'm again not keeping an eye on the. Yeah, so this was. I just want to.
Sorry, I don't know. This is too local for me.
Okay,
this is
sure.
something I
That's
wanted to
something,
put for the reference, but I don't know the details of that particular measurement.
Yeah, this Stanford drop tower, that is 10 to the power minus 12 for equivalence, this Kasevich group, which drops
again,
it for
that's not the local G measurement. Again, I know what you're talking about. This is this Bose-Einstein condensation business, right? Yeah. Thanks. Yeah, I'm taking.
So about the mapping the dark matters, so is it so what are the inputs that are using? One is the redshift, right? But is it enough to have a 3D map of the dark matter, or we have to take another few more assumption that along the more visible matter means it would have more dark matter also, or is that redshift is enough?
So there are multiple ways to map dark matter. The one I showed in terms of 3D images, what you need is a 3D structure. So you need to know what the 3D structure is looking at. So you need a space. So 3D means 3 coordinates, right? So for a galaxy, you need RA and Dex, so right ascension declination, as well as redshift. So those 3 quantity gives you 3D structure if you want to use galaxies themselves. The other ways to map dark matter, which is through lensing, I told you, right? So if you look at the photons from the background and look at how much is the deflection as a function of epoch, that will give you average mass of dark matter in different region. But you cannot create you can create a map, but it will be very noisy, that kind of map. So the people do using weak lensing survey by looking at the distortion in the shape of either background galaxy or in CMB photon, we can create maps of dark matter. But these are integrated maps. So maps, these are not 3-dimensional map. These are integrated in the sense that what is total mass along the line of sight between whatever epochs you are measuring.
Okay. Are there any more questions? Yes.
So if there are any higher derivative corrections to Einstein equation, presumably that's too tiny to be observed at a scale at what you're describing.
Yeah, so far, I mean, those things are best concerned with gravitational wave experiment rather than cosmology. And I think, although I'm not expert, there are other experts in the audience from the gravitational wave. So far, they haven't found any significant higher order correction on GR from this gravitational wave constraint. Cosmology is too weak for that kind of modeling, because really the strong gravity regime dominates there.
Thank you.
Okay. So if there are no more questions, let's thank Shadab again for a very nice talk. Oh, there is a question. Okay, I'm sorry. Maybe before we Thank him. Alok, you can actually use the mic. Alok?
Sigma attention, can gravitational wave astronomy shed light on
Okay.
the same question? So this is again, I'm not expert on gravitational wave part of it, but I've only heard a gravitational wave can measure Hubble constant very well, but I haven't really heard much. Like gravitational wave alone can do sigma, but what I've seen is that if you can do weak lensing gravitational wave cross correlation kind of analysis, so weak lensing combined with gravitational wave, there are a couple of people claiming that you can, and this depends on whether you are looking at bright siren or dark siren. There are a couple of people claiming that you can constrain sigma 8 very well with that kind of measurement.
Okay. Well, with that, we will close the colloquium. Let's thank Shadab once again. And all of us can join for some snacks with Shadab. So outside the canteen. Thank you.
Thank you. It was my pleasure. I hope it was not.
I just want to thank everyone, including the auditorium staff, for putting this together. So thank you, Ms. Riji and everyone. Thank you.
So then these are not anywhere close to.
This is just following the distance, we will not have moved over last
Decades, right?
decades. Since 1969.
So almost a century now.
That's an important yes. Yeah, that's why you